All right, we're going to go moving on to the last one of our first part, and that's the X-Inator.
All right, so we're X-Inator, and we'll be powering the future. And I am the co-founder, and I'm Hridesh, and I'm a computer engineering student at EUC, an undergraduate student. And here we start. So what's our problem statement? So let me put it in a small example. So there's a lot of battery packs in cars, for example, and the reason that EVs or electric vehicles take so long to replace gas-powered vehicles, it's because of two reasons. One is energy density, which you can see as energy per volume or energy per weight, which is like watt-hour per kilogram. And the other reason is because of safety concerns. Obviously, because certain batteries can only operate at a particular temperature range, and once they move further than a temperature range, there's more likely for fires to be occurring. And also you can see that gasoline is actually 60 times more energy dense than like batteries, which means batteries have a long way to go to actually catch up. So what would happen if we meet this demand? So first thing is you'll get longer range, high performance electric vehicles. Second thing is you'll be seeing electric planes or like electric aircrafts. Third thing would be further and further space exploration, which is basically because the further and further you move away from Earth, it's going to get colder and colder, and cells or batteries can't operate at extreme temperatures. And of course, last but not the least, is quicker path to renewable energy. So I'm going to start with basic fact, which a lot of people misunderstand, including me, before I got involved into cell manufacturing. So one is the difference between battery and a cell. So battery is pretty much just a combination of cells put together, connected together, and cell is the individual unit, as you can see here. And cell is composed of three different components. One is the anode, separator, and the cathode, and there's of course the electrolyte. So what's a solution? So a solution is a cell design which can actually have a high energy density, which we are predicting to have at least 5 times more energy density than the current high performing cells. And of course, we want it to operate at a broad temperature spectrum, ranging what we predict is because the material that we're going to use has insane temperature properties, which means we could operate anywhere between negative 500 degrees Celsius to 1,000 degrees Celsius, which is like a lot more better temperature range than like 0 degrees Celsius to 45. So market size. So the total addressable market, which is about $110 billion, is the entire battery industry. And however, we're going to focus just the small part of it, which is the military and aerospace, and that's about 0.3 billion. And you can clearly see the growth rate is pretty high, which is 25%. And of course, there's the new market because there's a lot of technologies that can't be developed because batteries lack like a high energy density. So of course, when we have high energy density, new technologies come in and hence a new market. So what's our product goals? So 5 times energy density at least, and solid state electrolyte, meaning there's going to be less chances for fires. And how do we do that? It's the way you start from scratch. So like you basically alter the whole structure of where the cathode and anode is actually stored, which is pretty much the cathode and anode is what defines the energy that can be stored in a particular volume. Because the more cathode and more anode you can store in a particular volume, that means the higher energy you can store. And electrolyte pretty much tells you the energy flow rate, like how fast your energy can flow in and out of the battery. So space industry. So that's where we're going to target, just like I mentioned. It's because we actually predict an expensive manufacturing process for a product, which means we have to target customers who can afford our product, which is the space industry, because anything you want to put it in space, it's super expensive. For example, $2,700 per kilogram, which is pretty insane. So yeah, and also, of course, our low weight cells can easily be the first choice for electrically powered aircraft. So what's our timeline going to look like? So first, we're going to manufacture that structure that I just talked about, and we're in process. Gonna get it done by December. And moving on, we're gonna coat the structure that we made with the cathode and anode and electrolyte materials. And moving on, that's gonna be the challenging part, and that's why we predict a longer time frame. And our goal is to build a functioning cell by May. And moving on, we want to build a cell cycler, which is used for cell testing to check its performance, etc. And after that, we're going to do data analysis to compare our cell performance with our competitors. And if it doesn't perform well, or if needed, we have multiple things that we can alter in the structure that can actually change the performance of our cell. So this is a bunch of major electric car companies. Okay, yeah, this is a bunch of electric car companies that you can see like what's the cost per energy and what's the energy per kilogram they can store. And our initial prototype, we're predicting to be expensive, of course, so it's going to be up there, but however, it's going to have a higher energy density. But future, once you start scaling, it's going to be a lot more cheaper. So what's our team and how we can actually do this? Me and my fellow co-founder, we both worked at Tesla as interns, and we worked about half a year at cell manufacturing department for the Cybertruck. And I was able to change the cell design to increase the Tesla's discharge and charging rate by 2%. And of course, my fellow co-founder has done good achievements as well. And we have a chemical process lead who's full-time in Jetson Engineering. And we have Will Mattis, who's the manufacturing lead, and he's been working at Thermo Fisher intern, as a Thermo Fisher intern. So what's the current progress? One is we secured funding for our initial materials, with which we can make about 4 gallons of our structure. 4 gallons is pretty huge. We just need this size to first test the cell. So yeah, we have multiple trials that we can do with the 4 gallons. And we have secured workspace, meaning we started assembling our materials to make our structure by December 2023. And what's our ask? So we need help with industrial marketing, anywhere in the military or aerospace industry. And we want to expand our connections with the cell research and development. Of course, we know some people at Tesla. I also have connection at SpaceX, but we'd like to know more. Never say no to like more connections. So we'd like to have more, and then strengthening chemical industry connections, because of course we are handling a lot of chemicals, meaning we want to, like, in the future we want to make it cheaper. In the case that we want to like have partnerships with chemical industries or whatnot, and then of course patent filing, because we're developing something new and we are undergrad students and we have zero experience patent filing. So we want to make sure that our product or our idea is not, of course, stolen by someone else. But yeah, that's pretty much it. Thank you.
All right, great job. Who has a question? Any questions?
How did you come up with this, and why, like, how is this so revolutionarily different than what there is today?
So we all know that, again, electric planes don't exist and flying humans don't exist because you cannot pack enough energy in a small volume so you can power these aircrafts or humans. So one of the one of the main problems, just like I mentioned, is having this challenge of packing a lot of energy into a small volume. And a lot of battery companies, they exist, and we have a lot of competitors, and they've been working on multiple battery designs. However, they haven't worked on something that's from scratch, which is like altering the whole structure, which encompasses the anode or cathode material that I was talking about, which is what we're doing. We're gonna alter the entire structure and try to pack in as much as the anode or cathode powder within that structure. So we pretty much altering the structure to have a higher energy densities. So.
So in particular with your aerospace application, the make or break for a lot of the designs that are coming out isn't just the weight and the energy density, but the turnaround time. Does your design allow for faster recharging, so you're getting it into the single-digit hours versus 12 to 18 hours that it may take now?
So if I got your question right, it's about the issue of charging speed. I wasn't able to hear you right. So was it about charging?
Yeah, about the charging rate.
Okay, so how cells work is either you can have multiple ions move ions as in electrons, so you can have them move really fast, or you have a lot of them move really slow. So what we're doing is having a lot of them move really slow. So we're predicting to have a higher charging and discharging rate.
All right, thank you so much. Great job. Woo.